Rightio. G'day everyone. We're going to have people, hopefully we've got a number of people in the waiting room, but we're going to get underway. This meeting is being recorded and will be available in Mighty Networks as of tomorrow. So if you're joining a little bit late, don't worry, you can catch up on the start tomorrow or another day. So g'day everyone. For all of the participants, I'm the familiar face from up in Dongra, and on the line we also have Dr. Ian Smith, and we also have Hayley online, who's our logistical legend. So welcome everyone. First up, I would like to acknowledge the country on which I'm situated at the moment, in Boorloo or Perth, of the Whadjuk Noongar people. And I would also like to, just acknowledge and call out that we're all dialing in from different places and different time zones, I should add, from right across Australia this evening. I would like to acknowledge the traditional owners of the lands on which we meet, work and live, and recognise that this land has always been and always will be Aboriginal and Torres Strait Islander land. We recognise the continuing connection to land, waters and culture, and we pay our respects to elders past, present and emerging, and as Whadjuk Noongar people say, Buddha, Nitcha, Buddhawan, Buddhiya, to elders past, present and emerging. I would also like to acknowledge the program partners of the Drought Resilience Leaders Development Program. And this webinar does form part of this particular program, and each of the regions are also having their own climate science webinar. So the Australian Rural Leadership Foundation, in partnership with a number of organisations, and bear with me as I list them through, the National Farmers Federation, so NFF, the Foundation for Rural and Regional Renewal, FRRR, the Rural Economies Centre of Excellence, RECCE perhaps, the Australian Resilience Centre, University of Southern Queensland, and many other partner organisations as well. We truly value the working relationships that we have with these organisations and their work across rural and regional Australia. And as we're probably all aware, but I will state it again, that this Drought Resilience Leaders Development Program is one program that is being funded through the federal government's Future Drought Fund. So before we get too much further underway, just a bit of housekeeping. For those participants that are online with us, please pop yourself on mute and ideally keep your cameras on so we can see your beautiful smiling faces. There will be a Q&A at the end. We can, I will invite you if you'd like to ask a question. Either there's two functions we can do it through the chat box, so just pop your questions in there, or raise your hand and I'll go around the Zoom room to prompt any questions that you have for Dr. Ian. In the interim, if you could just jump in the chat box to get our typing fingers warmed up and pop, please introduce yourself and pop which country you're zooming in from in the chat box. As I mentioned before, the recording will be available on Mighty Networks tomorrow. So for those that are joining late or aren't able to join us this evening or would like to watch it again, that link will be made available as of tomorrow. So only other piece of housekeeping that I would like to mention is whilst we have a very unique Northern Wheatbelt region for this Drought Resilience Leaders Development Program, Dr. Ian will be referencing locations in both of, those sub-regions, the Midwest and the in the Wheatbelt rather. So if there's a kind of some externalities to the two regions, it's just to kind of really the locations are to get an understanding to put this in context. So I would love to introduce Dr. Ian Smith, who is a highly regarded, highly experienced climate scientist and lecturer who spent many years working at the CSIRO and the Bureau of Meteorology, a website which I'm bom.gov.au. I'm certain many people have visited for a rain radar or two over the years. He has published, Dr. Ian has published extensively in the scientific literature on climate variability, climate change, climate prediction, and long-term climate change projections. He now runs a small consultancy and he works part-time for the UniSQ, so University of Southern Queensland's Centre for Applied Climate Sciences. Dr. Ian also has a brain twice the combined size of the Wheatbelt and Midwest and has much to share with us this evening. And so Hayley, who's the logistical legend behind the scenes, has said this same session in other regions has gone a little over time. for other regions. So you do not feel obliged to stick around beyond 8 o'clock, but Dr. Ian has generously offered to stick around for it to ask any other final burning questions, albeit it's very late where he's calling in from. So once it ticks over to 8 o'clock WA time, we'll kind of flag that, and those that do need to leave can absolutely sign off Zoom. So that all of the formalities out of the way, I would now like to hand over to Dr. Ian.
Oh, look, thanks very much for that kind introduction, and welcome everyone, and thanks for tuning into this talk. I think you should all be able to see the first slide here, which is the start of the talk. I'm talking to you from Melbourne, and I'm dealing with a rather large topic, which is past, present, and future climate for Australia, Western Australia, and with a bit of a focus on the Northern Wheatbelt. Now, some of the material I'm sure you'll all be familiar with, but it doesn't hurt to revisit some of these topics and to give everyone another perspective on climate change, the what and the why of climate change as it relates to them. And the talk is based on what really information that's already out there in the public domain, in publications put out by various organisations, including the International Panel on Climate Change. I'm sure you'll all have heard of that, the Bureau of Meteorology, the federal government and state governments all produce information. So this talk will draw on those resources, and as I say, I'll try to make it a little bit more topical by supplementing what's been put out there with a little bit more of recent information, particularly because whenever you look at climate and climate science topics, you realise that day to day there's a lot of information coming out in the media. There are reports of events, including the floods in Queensland and New South Wales, new records for heat waves, etc., and lots of discussion about projections for climate change. So the topic is somewhat dynamic. So I'll try and provide you with a little bit of updated information that helps you in providing a perspective for you. So I'll be talking mainly about, when I talked about climate, I'm going to focus on just the key variables, temperature and rainfall, and I'll try not to dwell too much on the impacts associated with changes to those two variables, because follow-up sessions will be dealing with that. It's a huge topic in itself. So when it comes time to consider what options are available or what strategies are available to people to adapt to climate change, if not mitigate climate change, that's for another session. And hopefully my task is to get through this material and leave time for questions. So let's get cracking. As you already know, that's my current affiliation. When I worked for CSIRO, one of the projects I worked on was in cooperation with the West Australian government, particularly the Water Corporation. This is going back quite a while now, when they were interested in researching why the runoff and the rainfall into dams around Perth and Perth catchments had declined, and what they could expect for the future. And I must say that was a very enjoyable collaboration I had when I was working with CSIRO. I should mention the contributions by colleagues, Scott Power, Kate, Sharmila and Nina from the UniSQ. That's greatly valued. And as I say, there are various sources available, and here are some of the publications that people can look at to fill in or get extra information about the material I'm talking about today. And as I say, it's a dynamic topic, and just recently, here are a couple of things that have been put out either on the Twitter sphere or in the media, but they're well worth noting. Brisbane has just had its wettest 3-day period on record, breaking the previous record in 1974. That was put out by the Bureau on Sunday evening. And a person who lives in Brisbane has made this comment about what's happened there. I grew up in Brisbane and the 1974 floods were rare. Now we have had 2011, 2013, 2017, and 2022. So that's an impact of changes in rainfall, or in particular changes in rainfall intensity that have occurred up there. And when we come to Western Australia, just go back to January the 25th, Perth smashed its previous heatwave record last week after 6 days in a row over 40 degrees. That makes 11 days over 40 degrees this summer. The impacts of this includes widespread power outages and bushfires to the north. And it's worth noting that Southwest Australia is considered a hotspot for climate change, as the long-term warming and drying trend is extremely pronounced. This makes this particular part of Australia a little bit unique compared to other regions which I've been talking about. Other regions, the evidence for climate change in the recent past is not so great. But on the other hand, other regions are significantly affected by interannual variations due to El Nino, La Nina events, which in one sense, they benefit from being affected by ENSO because it means it's possible to make predictions for rainfall and temperature when you know something about El Nino and La Nina events and when they're coming and how strong they are. That's very different to Western Australia. The effect of El Nino, La Nina is not that strong, but the influence of climate change appears to be much more evident over there than elsewhere. So the talk is divided roughly into two halves, the past and the future. And the first point I make, especially for people who are, as I say, living in parts of the country where El Nino, La Nina events dominate, is that the rainfall pattern across Australia is highly variable. It's one of the driest continents on the earth, but the rainfall, the variability in the rainfall is one of the highest on the globe. And this is a series of maps showing the picture of annual rainfall anomalies over the past 50 years, starting from the top left-hand corner at 1970, progressing right through to the bottom, that's 2021. And you can see lots of variability, lots of ups and downs. And the task of climate scientists, when they look at this, all this data that lies behind these maps, is to, first of all, identify patterns or signals which may be useful for predictions. And that's where the studies of El Nino and La Ninas comes into play. You can see the effects of El Nino and La Nina events within those patterns. And on the other hand, there's also evidence of trends in some of the rainfall patterns. And I'd like to draw your attention to the map on the bottom right-hand corner. This is the rainfall anomalies for 2019. Now, this is an unusual, particularly unusual year, because that was officially the driest year on record, on average across Australia, and also the warmest year on record. And you can contrast that, if you like, if you go along to the left of that row, back to 2010 and 2011, which were, that was during a La Nina phase when wetter than average conditions prevailed over much of eastern and northern Australia. 2019 reflects the effects of El Nino type conditions, plus it's also reflecting what we think are the effects of long-term climate change. Now, if you were to average the rainfall across the whole of the Australian continent and calculate an average and plot that as a function of year, the annual totals, in this time series graph here, you can see how the annual totals across Australia have changed from 1900 right through to 2020. And again, it serves to illustrate the large variability, and also it provides evidence for the effect of El Nino, La Nina events. And you can see them in the unusually wet and the unusually dry years. Studies have looked at the patterns and these types of time series, and interestingly, they suggest that overall, on average, the continent is getting wetter overall, but I'll return to that topic when I discuss long-term trends a little bit later on. Now, as I say, you're probably very familiar with El Nino Southern Oscillation events. So I'm going to skip over this very quickly, and just to note that ENSO is how we refer to it, that the phenomenon is a combined fluctuation of anomalies in both the oceans and the atmosphere. The acronym ENSO, the EN stands for El Nino, and El Nino refers specifically to the sea surface temperature anomalies off the coast of South America. The SO in the acronym stands for the Southern Oscillation, and that refers to the anomalies in the pressures at both Darwin and Tahiti. So the ENSO phenomenon is described by various indices, which refer to both the sea surface temperatures and the Southern Oscillation, or SSTs and pressures, as we like to talk about. And again, this is a diagram illustrating why the atmosphere and the ocean behave in a coupled way. And I'm going to be very brief. The right-hand figure here is a La Nina type situation, which occurs when we have warmer than average temperatures to the north of Australia. That enhances convection and leads to increased chances of rain across northern and eastern Australia. And the right-hand map is the opposite phase of ENSO, the El Nino phase, when the opposite occurs and we experience less rain over this side of the Pacific. And when we look at the what the impacts are on the pattern of rainfall across all of Australia, we can look at those years where La Nina conditions prevailed, or and vice versa, all those years where El Nino conditions prevailed, and you can come up with these maps. And the one on the left tells you where you can expect above average rainfall when you're in the La Nina phase, and vice versa, where you'd expect drier conditions to occur during the El Nino phase. So the impacts of El Nino and La Nina, or ENSO events, are widespread, but they tend to be concentrated to the north, the central and the eastern half of the continent. If we look at those circles that I've drawn on the maps, which approximately correspond to the Wheatbelt regions, or Southwest WA Wheatbelt, you don't see much of the colour coding coming into that area, which indicates that ENSO is rather is not a significant. It doesn't have much of an impact on rainfall over your part of the world. There's another influence on rainfall, which is referred to the Indian Ocean dipole. Again, it doesn't have much of an impact over your part of the world, and it only affects winter spring rainfall. So I won't dwell on that at this stage. And so after talking about all the sea surface temperatures, this map tells us what's happening right at the moment. This is a map of the sea surface temperature anomalies as of just over a week ago, February the 21st. And you can see patterns of anomalously warm and cooler waters across the globe. But if you just focus around the equator, you'll see a typical or a classic La Nina situation where you've got the warm anomalies to the north of Australia and the cool anomalies over in the Eastern Pacific adjacent to South America. What has been the impact of those anomalies? I just should point out that these anomalies are long lasting. They don't just come and go like the weather does on a daily basis or a weekly basis. These anomalies, once they set in, can last for several months, and a typical El Nino or ENSO event will last for something like 12 months. So once these patterns are set in play, then you can see their effects in seasonal rainfall anomalies, such as this map produced by the Bureau. It shows for the 3-month period, or the summer period ending on the 28th of February, that's the summer period just passed, the impact, well, not so much the impact, but the rainfall anomalies experienced across Australia are shown in this map of deciles, which I assume you're probably aware of. And you can see the bluer regions corresponding to above average rainfall. You can see the impact of La Nina type effects, particularly through Central Australia and over into New South Wales, Southeast Queensland. But it's not everywhere. It's not a consistent signal, but it is there. And over in Western Australia, you can see that the summer, despite it being La Nina conditions, summer has been, according to this map, relatively dry. And if you want to look at the outlooks for the March to May period, this is what the Bureau suggests might happen. This was issued a week ago. And the green and bluey regions indicate where there are shifts towards above median rainfall over the next 3 months. And again, in southwest WA or the Wheatbelt region, the circle there indicates there's not much of a signal, because the colour there is white, meaning there's no evidence of a shift either way. So just to summarise that brief excursion into interannual variability, the summary, the major points to take home are that rainfall is extremely variable in Australia. Some of this variability is related to the variability of ocean temperatures in the Pacific and Indian Oceans. This allows seasonal rainfall outlooks to be regularly prepared, but there is not a great deal of predictability over southwest Western Australia. So, moving on to the next part of the talk, how has climate changed? And I think, again, this is more of interest to people in Western Australia. First, we'll have a look at annual global mean temperatures, and you may have been familiar with this particular time series. It's the annual global mean temperatures expressed as anomalies since 1880 through to 2020, as best as can be determined by careful analysis of thermometer readings over land and taken over the oceans for well over 100 years. And what you see here is a tendency towards increases or increased temperatures towards the end of the series. And I should also point out that if you look at this very carefully, you can actually also see the impact of El Nino, La Nina events on global average temperatures. And that just highlights how important that phenomenon is on a global scale. But based on all the available thermometer evidence, it's been carefully ingested and analysed by scientists for many, many years, including the results of satellite observations. it's fairly clear that there's been a warming trend, particularly since the middle of last century, of the order of a degree or more. And the science is pretty much settled on this because the Intergovernmental Panel on Climate Change states very, very strongly scientific evidence for warming of the climate system is unequivocal, despite what some people you might come across claiming that it's all fake, it's all made up. If you needed any more evidence that the whole globe is warming, you only need to look at what's happening in other parts of the environment. And you can see the impacts of warming around the world in a whole host of elements, including the melting of glaciers, for example, in New Zealand, in New Guinea, in the United States, Greenland. You can see it in the reduction in sea ice, which is floating ice around, which is important in the Arctic and Antarctica. Right at the moment, the sea ice around Antarctica is at its lowest level ever. And there are other impacts where you can detect global warming in terms of shifts in tree lines, species migrations, increases in sea level. So the point here is that if there's any doubt about global warming, you only need to look at the impacts, and these are all well documented and quite robust. What about in Australia? Well, again, I'm showing you a time series here of temperature anomalies based on the temperature record averaged across all of Australia since 1910. And the time series extends from right through to 2020. And what you can see here is, again, almost it's very similar to the global annual average temperature in that the temperatures have warmed fairly significantly since the middle of the last century. And I should also state again that even when you average the temperatures across Australia, you can still see in these time series the effect of El Nino, La Nina oscillations. And if you look up at the end of the time series, you'll see the maximum value there on this time series of plus 1.5 degrees. That corresponds to that landmark year 2019. Let's go and focus a little bit more on what's happening in the northern Wheatbelt regions. And again, I'm showing time series of annual mean temperatures, and these can be accessed from the Bureau of Meteorology website, but we've extracted our two time series showing how annual temperatures have varied over the long term for both Merredin near Munkinbudden, which sounds fascinating. And the other one on the right is the time series for Geraldton Airport near Mingenew. And if you can see the maps, you can see the little red dots, which indicates those locations for those people who may not be aware of them. Now, the interesting thing is that the time series for both these stations represents thermometer readings over all those years. There are some gaps in the time series, and you can see gaps where, for one reason or another, recordings weren't possible. But despite those gaps, if you look at the time series, you can see a trend in both of them. They're both independent sites. You can see an increase of the order of about 1 to 2 degrees over that 100 years. So it's very clear evidence of a warming trend for these particular locations. And again, well, not again, this is now a map of the trends in temperature across Australia based on analysing the temperature records from a whole host of sites, including Merredin and Munkinbuden. I just have to say that, Munkinbuden. And so the two black circles that on the map indicate the approximate locations for those sites. And the trend map for Australia shows mainly red and pink, which corresponds to long-term increases in temperatures. And the general pattern here is one of larger increases inland and slightly smaller increases around the coast. But everywhere, bar a spot in the Northern Territory, has warmed over the period which this map refers to, which is the past 50 years, 1970 to 2020. What about rainfall? Mingenew, we could also, anyone can dial up this data from the Bureau of Meteorology website. And this is a record of Mingenew, which I've spelt wrong in the header, I apologise for that. Mingenew annual rainfall totals from around about 1900 right up to 2020. And again, you'll see some gaps in the data because sometimes it's not possible to provide a continuous record due to a whole host of reasons. But as far as we can tell, this represents a pretty good indication of the long-term rainfall at Mingenew. And the two things to note are that it's highly variable. The long-term average is about 400 millimetres. In a very wet year, it can almost double. In a very dry year, it can almost halve. But if you look at, say, from the period 1970 to 2020, the last 50 years, you can discern a downward trend in the data. And the question mark there says, well, it does appear that the last 50 years on average are drier than, for example, the previous 50 years or the earlier period. Careful statistical analysis of data such as this does show that there has been a downward trend over the past 50 years. And if we look at the map of rainfall trends from all the stations where rainfall data is collected, you can draw a coloured map showing the trends across Australia for that 50-year period. And Mingenew is indicated by the black dot there. And you can see it falls within the pale brown or pale orange area, which corresponds to long-term decreases in rainfall. So that time series I showed you before is consistent with the map that the Bureau has produced. And the two things to note about this map is that a large part of Western Australia and Northern Australia has been getting wetter over time, and that is particularly unusual when you analyse it. Much of Eastern Australia has been, over that 50-year period, been getting drier, and not all of that is statistically significant. But I should point out in southwest WA, even though the drying trends there around Perth and the northern Wheatbelt, they don't look particularly strong, but they are definitely significant and have had quite significant impacts over the past 50 years. Now, if we focus a little bit more on the rainfall in your part of the world and look at just Mingenew June rainfall, this is June is when that time of year when it typically gets its maximum rainfall out of all 12 months, we can also plot what's happened. And this is quite interesting in that if you look at the data and plot the data and look at what's happened over the last 50 years compared to the earlier period, that red arrow points to a quite definite downward trend in June rainfall. And the exclamation mark I've put on the time series plot indicates, yes, that's quite unusual. It's not an artifact of the data. There has definitely been a change in June rainfall at Mingenew over the past 50 years. And the impacts of that may or may not have been severe. So to summarise what we know about recent climate change in Western Australia, on average is warmed by about 1.3 degrees. The rainfall has increased over most of Western Australia, but has declined in the far west and southwest. One of the impacts of the warming, at least, is that the number of days with dangerous weather conditions for bushfires has increased. And another thing that has been noted, which I haven't talked about till at this stage, is that the number of tropical cyclones has declined over that period. And that's true of Western Australia, and it's also true of Queensland and the other parts of Australia which are affected by tropical cyclones. And it's worth noting that we think that's partly tied up with climate change. It's one of the impacts of climate change which people are still trying to get their head around and explain, but it is a definite signal. After having looked at all these changes in temperature and rainfall and other parts of the climate, the natural question is, what has caused the changes? And what scientists do is to resort to climate models, which are the same as the weather forecast models, which produce your daily weather forecasts, produce those maps of pressure patterns and winds and rainfall patterns that you might expect over the next few days to a week. Essentially the same models, except they run for much longer. They run for tens, hundreds of years, with various inputs driving them over that period. Three main inputs to the climate modelling when it comes to climate change are the three factors which we think are most important. It's variations in the sun, variations in the amount of gunk in the atmosphere due to volcanic eruptions, and the amount of carbon dioxide in the atmosphere. Variations in the sun do occur. They're not very large, but they do happen to occur on decadal timescales. Variations in gunk in the atmosphere has the effect of introducing a cooling element. When you get too much gunk being emitted into the stratosphere and the higher atmosphere, it does reflect some of the sun's radiation back to space and has a cooling effect. And carbon dioxide is as an insulating effect, which acts to warm the climate. So we know the effect of these three things, these three drivers over the past 100 or so years, and we can feed them into climate models and try and explain what's happened over the past 100 years according to the climate models. And as I say, the three drivers, this one is the amount of carbon dioxide in the atmosphere. It has been observed. It shows a steadily increasing trend. Since 1960, it's increased by about 30%. That's quite a significant increase. And what I'm going to try and describe to you now is the results of experiments with the climate models where they've played around with those inputs, the three inputs, suns, volcanoes, and CO2. And what they've done is they've started the models back in 1850. They've run them forward in time with the known drivers over that period. And they look at the results and compare them with the observations. Now, in this graph, we have observations of global average annual temperature indicated by the black curve. And we've got two sets of model results corresponding to two sets of experiments with the models. The green part of the graph corresponds to the results of experiments where you just provide the climate models with the effect of variations in the sun and the effect of volcanoes. And the results from those model simulations include variations in the global average annual temperature, but towards the end of the time series, there's no way they can explain the observed record, which is the black trace. And the second set of model experiments is when you include all three drivers. You put the CO2 driver into the simulations, and you end up with that pale brown results. And you can see that the pale brown trace of global annual average temperature is almost slap bang on the compares very favorably with the observations. So the take-home message from this type of work, and which provides confidence for when we look to the future, is that despite people complaining that the observed warming is the result of changes in the sun and sunspots, or it's due to changes in the volcanoes, or it's due to changes in some other factor, this provides fairly solid evidence that none of those things can explain what we've seen to date. Only the inclusion of increasing carbon dioxide concentrations can help explain the observed warming. Now, this comparison here is of great interest because we're looking at rainfall now. And the question is, can we explain the pattern of rainfall, the rainfall trends over Australia over the past 50 years? So the map on the left I've already shown you. That's the trend map for rainfall over the past 50 years. And the map on the right is the output from climate model simulations at a point in time, some point in time in the future, where the globe has warmed up by about 2 degrees. And the color coding is very similar. The brown and pale brown colors on the left contrast with the green values, which represent increases. And the model results for a +2 degree warming show brown and pale brown, or I'm not sure what color that is, a pattern around parts of Eastern Australia, Southeastern Australia, and Southwest WA, which contrasts with increases over much of the interior of the continent. Now, it's not a perfect match. We don't expect a perfect match, but the similarities are sufficient to enable us to be a little bit more confident in saying that the trends that we've seen, such as on the left-hand side, may be due to the global warming that we've experienced up to date, even though that map on the right is for some time in the future. This provides us with an indication that we might already be seeing the effects of global warming in our rainfall maps. Keeping an eye on the time, the future, what is projected for the decades ahead? And I think you will understand that having done those experiments to try and explain the past, we run the models forward in time where we increase the greenhouse gas concentrations. We don't know what they will be exactly, but the climate modelers put in a range of scenarios of various greenhouse gas concentrations, some increasing dramatically, some increase and decrease due to assumed restrictions in fossil fuel burning. A whole stack of those experiments have been performed, and the results of the model for global average temperature going out now to the end of the century are shown in this time series, and the different coloured traces correspond to those different greenhouse gas or the different carbon dioxide concentration time series. Top one is unchecked growth in emissions, or no change to what we're doing now. We would, according to the model, be heading to a warming of 4 to 5 degrees. And the bottom one, the blue trace, indicates what we might be able to achieve if we introduce strong cuts to emissions maybe zero emissions by 2050 or even earlier. And governments around the world would rather we track the blue curve, because the blue curve suggests we can restrict the warming to levels which we can cope with. That's why the governments have adopted the goal of zero net emissions by 2050 and so on. I'm showing the results of those simulations by the climate models on a global scale. They just show you the general warming that occurs when it reaches +1.5, +2, or +4, and you can see things getting worse depending on how warm it gets. The same for rainfall, +1.5, +2, or +4 degrees. You can see the impacts on rainfall across the world according to the models. And the map I showed you earlier comes from the centre. It's the centre map where I've cut out the bit focusing on Australia. And you can see that even at 1.5 degrees, if you could look closely, you can see that pattern of warming off the southwest, slightly wetter inland, drier in the east. The same at +2 degrees, and it's the same at +4 degrees. It's a fairly consistent signal. In conjunction with changes in average rainfall, we expect rainfall to become more intense. And that's because we know that as you warm up the atmosphere, it can hold more moisture. And so when it comes time to release that moisture in the form of a rainfall event, there's much more rain falling in a warmer atmosphere than a cooler atmosphere. And the results from the various studies suggest that if you've got a warming of about 4 degrees, which is something we would not like to achieve, that the intensity of rainfall could go up by 30%. Now, I'm not sure how much that's an issue for the northern Wheatbelt. And on this particular time series, what we're showing is daily rainfall amounts measured at a site, the Minginyu post office near Dongara. And forgive me for my lack of familiarity with the names and the locations, but this again shows what I'm trying to show here is if we look at the current record of daily rainfall events showing, in 2000 there was a daily rainfall amount of 120 millimeters. That was the highest one in that particular period of time. And you rarely get above 80 millimeters, but you do get quite a few above 40 and 30 millimeters in a day, despite the relatively dry nature of the climate. And the little red bits added on top of the blue lines correspond to a 30% increase on those particular dates. And the question is, going from say 120 to maybe 150 or more or going from 80 to 100 in daily rainfall amounts. The question is that a serious impact for the northern Wheatbelt, or is it something they could cope with? And I'll leave that discussion for the follow-up session on impacts. Now I'm straying a bit away from the regions, but I should point out that even though tropical cyclones have decreased in number over recent times, the recent experience with tropical cyclone Anika was only category one cyclone according to the Bureau, yet it generated quite a lot of rainfall in a small region into the north of WA. In fact, for this, if you look at the amounts that fell with that particular tropical cyclone, they correspond to well over 100% or 150% of their of what they'd expect for the whole month at this time of year. So that one event has generated quite an amount of rainfall. And again, that might be partly due to what we've been talking about. The increase in intensity in a warmer world may mean that you might get, for example, lesser tropical cyclones, but when they come through, they're going to dump a lot more water. So I'm going to quickly skim through the projections for WA, and forgive me for doing so, but you can find all this information on site and consider it in more detail at your leisure. But for Western Australia, under a high emission scenario, average annual temperatures will increase by another 1.5 to 2.5 degrees. Impacts of that warming will be an increase in the number of very hot days. Typically in Perth, they get 1.5 days greater than 40 degrees in a year. They could increase to 5 days. Or if you're in Broome, it may go from 6 days a year to 16 days per year. And the only way to avoid those sort of impacts is to adopt a low emissions aim for zero net emissions and a reduction in the amount of CO2 going forward. Some more impacts and things to expect for Western Australia. The climate of Perth may become more like Jurien Bay. Albany may become more like Busselton. Broome might become more like Derby. Longer fire seasons, increased sea levels, that's almost certain. Extreme rainfall events to become more intense, which I've just discussed with you. On the whole, though, Southwest WA is likely to become drier. Rainfall change in the monsoonal north is unclear. And if you want to look more closely at what's projected within your region, then there are sites and there are publications from which you can access to find out that, for example, the Northern Wheatbelt, you can see what the temperature predictions or projections are and the degree of confidence which is associated with those projections. For example, more frequent hot days, higher temperatures, min and max temperatures, decreased frequency of frost days. They're all highly confident about those projections. Ongoing decreases in winter, spring, and annual rainfall. Now it's interesting. There's high confidence in that trend continuing. Changes in autumn and summer rainfall are unclear. They're being honest that they can't be certain about what will happen there. The map on the right there is a hugely interesting map in that it indicates where the rainfall isohyets or where the annual rainfall zones are shifting, and comparing 2000 to 2011 back to the start of the 20th century. And I won't go into the details, but if you get the chance to look at that, it's very interesting, showing you that the dry regions are encroaching or moving towards the southwest. Other projected changes: increased heavy rainfall, duration of droughts. Again, we're getting into back impacts here: increased evaporation, harsher fire weather, higher sea levels and extremes, warmer and more acidic oceans. I'm going to almost wrap it up now, so we've got time for questions. Impacts on the coral reefs, both the Great Barrier Reef and the coral reefs around WA. They are at huge risk of warming, and that's just one of the reasons. Another reason why we should aim for trying to keep the warming that's coming to 1.5. Our effort should be to at least keep it below 2 if we can. The summary there is more or less repeating the points I've already mentioned. And almost the last point in this presentation I'd like to refer to is the fact that the IPCC has just released an assessment report within the last few days. And without having read it or delved into the details, the take-home message from this report is that the opportunity to deal with climate change, or the problem of dealing with climate change, is twofold. You either mitigate by reducing greenhouse gas emissions, and or you adapt to the warming and the climate changes that are coming. But the take-home message from this report is that the window for adaptation, your ability to adapt to what's coming, is becoming very short now. And as a society, we may be running out of time to make the necessary adaptations before the warming hits us. So I would like to end there and thank you again for listening, and I'm happy to take questions.
Fabulous. Thank you very much, Ian. A sobering snapshot, I think, is the word that I would say of what the past has shown, and what we can expect for the future, and then I guess some scenarios around what, if we do act, what it does look like. I have popped in the chat box whether anyone wants to ask a question, and I have had a question crop up from Kate. I also have a question from Roger. Thank you very much. I'll read out Kate's question. When talking about the percentage of carbon increase into the future, are these percentages measured from 2022 or earlier?
Are we referring to the observed time series that I showed, or to the projections of future CO2 concentrations?
Both, please.
Well, the observed one I showed you were the measurements from Hawaii, and there's no doubt about them, because they're measurements are made all around the world of carbon dioxide, and so we know the past is fairly well established. Going forward is the issue, and what's assumed is that it's a good question. The question I think relates to where do we benchmark? When do we start measuring the reduction in CO2 as a result of changes in emissions? I think that's what the question aims at. I think it would be, I'm going to have to chase this up to give you a correct answer, but I think that what the model experiments do is they start with the concentrations measured in, say, in those experiments, say 2015. So they'll begin with the observed CO2 concentrations in 2015. That's the starting point for the simulations. And then they assume certain behaviours by society in terms of do they continue burning X amount of fossil fuels, in which case after 2015 the CO2 concentrations will do this if nothing changes, or if they really cut back over the next 10 or 20 years, the concentrations from 2015 will keep increasing, but once you stop producing them, they won't go backwards. They will continue for a while until eventually they start to slowly decline due to natural processes in the system. So I hope that sort of addresses the point of the question. In generating those scenarios, those various curves, there's quite a lot of modelling involved, separate from the climate modelling, assuming, whether, for example, if China and America and India all stopped burning coal at some point, they try and estimate what the concentration would be in that scenario. And it's not a simple calculation. That's why a lot of work goes into generating those scenarios. which then the climate models take and use to drive the models.
Great. Kate has said that did answer her question, so thanks very much for that, Ian. I'm mindful that it's 1 minute to the hour, so for those that do need to jump offline, feel free to do so. I will just say before you do jump off though, that it was quite serendipitous that Cyclone Anika was mentioned, because in our session, our upcoming online session this week, we do have Dr. Anika Molesworth joining us online on the first afternoon from my vague recollections, but she'll be joining us. And we're going to be talking through, I guess, how it is that we use the knowledge that we have around climate science, albeit quite sobering, to have conversations that actually shift the dial. So I guess the old adage that it is better to know than not know, and not be that ostrich with it or emu with its head in the sand, is really the intention of this conversation. So I will see, for those that do need to jump off, feel free to do so. We'll see you online at 9 o'clock or just prior to 9 o'clock on Tuesday morning. I'm now going to throw to Roger, who has his hand up. So thanks very much, Roger. And then I've got another question from an online Q&A.
Thanks, Liz. Yeah, Ian, my question is in a bit of a similar sort of a theme to what Kate was talking about with CO2 and that sort of thing. There's been, and you're pretty big on your data, so I think this sort of fits with you, with the historical records from ice cores going back a long period of time. Where are we now compared to situations in the past with CO2 levels, which have then sort of resulted in tipping points where the environment corrects itself and that sort of thing? So where are we now compared to some of those events in the past?
A very good question, Roger. I would need to dial up, which I don't have on me at the moment, a slide which shows you the long-term record of CO2 concentrations. And the question of has it been, the question that's often asked is, are the current values unusual if you look in the long term? And I'm pretty sure they are. But I'd also make the point that even if there were, well, even if they were similar in the past, the thing that really is a worry is the pace of change, because they're man-made concentrations, or it's the humans who are causing this rapid increase in the space of decades. And the key thing is the pace of change, that they're going up so quickly, and the warming's going up so quickly, you can't find anything in the record, the long-term record, going back thousands of years where things have changed that quickly. So that's partly, it's not quite the answer you're after, but I think it might address what you might be interested in that the seriousness of the situation is not so much, well, it is the amount of CO2, but it's also the rate at which it's gone up. I don't think the Earth's experienced anything like this in the past. Yeah,
so the rate's unprecedented sort of thing.
Yeah. But I will get back to you if you don't mind. I'll get somebody to pass that on to you to give you a more definitive answer. Yeah, I do have that information somewhere in the form of the slides or time series. Yeah.
Fantastic. Thanks for the question, Roger, and thanks, Ian. And I love this question from Bron, to a climate scientist. So I'm interested in your response, Ian. So Bron says, thanks very much for the summary of the climate change predictions. And so her question is, what is the likelihood of the world halting CO2 emissions? Is the first question. Second question, what level of temperature increase do we need to prepare for?
Oh, thanks, Ron. The likelihood of meeting those targets, well, the governments around the world have agreed on getting to net zero emissions by 2050. And all the science says that that's necessary to keep the temperature increase to close to 1.5 degrees, which we can cope with that, or we can adapt to that. What are the chances of governments or societies achieving that? Well, ask yourself, how good are government projections in anything else that you deal with? I'd have to say that we're unlikely to reach zero net emissions. It's an ideal goal. Society is notoriously slow at making progress on these fronts, and they will probably hurry up the more and more significant events that unravel as we head through the next few years. Because, as I've said in a previous talk, governments will really only move or take hard decisions in the face of disaster. And unfortunately, we need a few more disasters to get them to move. So what's the likelihood we will get to zero emissions? To be honest, I don't think it will get to zero, but I think as the disasters unfold, that more and more people and more governments will start to make big efforts to, the penny will drop and they will definitely start to cut back their emissions. And so we may not get to net zero by 2050. That means we probably won't get to plus 1.5 degrees by the end of the century. Yeah, again, I'm giving you an opinion here, and I don't know that's I should be doing that at a government-funded talk. But seeing as you asked, I'd be guessing we probably have to aim for about plus 3 degrees, 2 to 3 degrees in the future. And all those predictions about the drying trends and that will be are probably very difficult to put a stop to, unfortunately. But the impacts, again, the next session in this series is where you can discuss the impacts and whether the impacts are really serious for your part of the world, or which impacts you should focus on adapting to. At the same time, I would hope you'd be lobbying or passing on to your fellow community members the urgency of doing the mitigation side of things, actually doing as much as you can to achieve those zero net emissions, while at the same time doing the adaptation side of things to ameliorate what's going to happen in the future. So I won't be in part of those impacts discussions, but I think they will be fascinating to be part of.
Thanks very much, Ian. And I, for one, appreciate your candour. And even though I was not expecting a climate scientist to offer personal perspective, I do really appreciate that, because I think that's part of, I guess, reality check for us. And I think by the judgment of Bronwyn, I hope you don't mind me calling this out, Bronwyn's audible eye roll when you mentioned about government targets, I guess the reality of that. Yeah, I think she also appreciates it. Now, I've got 3 questions lined up, 2 online and then 1 with Stu with his hand up. So I'll do 1 online, go to Stu, and then back to the other one. And I think the other one's a great question to wrap up this evening's, the final question's a great one to wrap up this evening's webinar for. So the next question is from Kate. Will localised revegetation and other mitigation steps lessen the extreme weather events at home, or is this only done through a whole world approach?
Will local revegetation, have an effect on extreme events? I think the answer to that is no. But on the other hand, the efforts to revegetate are important in their own right. There's a whole number of reasons why you'd want to revegetate. One of them being that it adds to the sink of CO2 in the atmosphere. So unfortunately, the increase in rainfall intensities is a function of the atmospheric temperatures, and the atmospheric temperatures are determined by the winds blowing over large areas of the globe or large areas of the oceans, and the local impacts on rainfall are relatively small in the face of these larger term impacts. So I would guess the answer to that, unfortunately, is a no.
Can I jump in? Because mine's a follow-up to that.
Yep, go for it, Stu. I can see you.
So, Ian, I was a bit worried my question was after yours, Kate, but yeah, mine's on a similar vein. And if I look at some of those pictures of the drying of the continent that you have shown, the most severely affected areas are actually the areas that have been colonised and cleared first from vegetation. And I'm not sure whether you're aware of some of the studies done out of UWA and on the effect on clearing on rainfall in West Australia. It is actually very significant. And you can actually still see there's greater rainfall on the perimeter of the Wheatbelt, or the area we're looking at, where the trees are. And trees play a very important role in creating the nuclei that allows the rain to drop. And there's been similar studies done in New Zealand as well. So I think that is really important. So it will have a localised effect. And I think there's circumstantial evidence even in the Wheatbelt now where there has been some tree plantings already, where there has been an increase in rainfall around those trees. But I think what we need to realise is that we've gone from a perennial landscape to an annual cropping system. And for a lot of other countries in the world that went to annual cropping systems, they actually do run 2 annual crops, so they are greener for a longer period of the year. Whereas in Australia, we have these big chemical fallows in between, which is actually heating up the land even more and absorbing more of that solar radiation. So I would really like to see a lot of that work included into the climate research, because, as you said, it's an important carbon sink as well. But if it can actually give us a more reliable and mitigate and even out that rainfall by actually creating some of that rain to come before we get these really extreme events, it may actually help moderate the rainfall as well.
Thank you for that additional information, Stu. Just before you stay off mute and put your hand down, did you have a question, or was it kind of just adding to the commentary? Or
well, my question to Ian was going to be, similar to the other one, but it was obvious that perhaps Ian may not have seen some of that research, or doesn't place the credibility that a lot of us over here place in it, I guess.
Yeah,
I'm quite willing to believe that there's something in what you say, Stu, in terms of comparing the climate around a large area, a forested area, comparing to the climate of a deforested area. Undoubtedly, you will see local climate effects because you're changing the surface characteristics by quite a bit. But the question whether you can ward off the larger scale effects that are coming is one which people should possibly have another look at. But as I say,
I think it would have to be. Yeah, I think it would have to be part of the whole systems approach. Yeah, it's not going to do it alone either, I think. So.
Yeah, the moisture that you get over you when it's going to rain, and the moisture is just blown in off the oceans, and then look, I will say this: there's definite evidence that if you look at the rainfall patterns around large cities, that there's more rainfall downstream of the prevailing wind than upstream. There is an effect of cities on local rainfall patterns. So you can see an effect, local effects on rainfall due to changing the surface characteristics. So I probably agree with you that there are localized impacts, but I'm not sure whether they're wide enough or sufficiently strong to overcome the large scale changes that are coming. But I would, I'm happy to have a look at some of that research. If you, I can look it up, but if you've got something you could send my way, I'd appreciate that.
Yeah, sure. Yeah, I could. And I think Walter Yeno would be a good person to talk to, ex-CSIRO scientist. And I think I've seen some stuff around the widespread clearing, because obviously vegetation transpires moisture as well. So it's a biotic pump. So it is responsible for cycling that moisture. And because of the widespread clearing up in Indonesia and further abroad in Borneo, some of those big forests up there are not doing it as well.
Yep.
I reckon we could do another hour of the Ian and Stu Power Hour that you guys could just bounce off each other for forever. I'm going to put a pause. Stu, thank you very much for offering to send through that information to Ian. Ian, I know Stu very well. He is a walking encyclopedia that has a brain equally as large as yours in the Wheatbelt and the Midwest. Final question.
Cut it out.
Final question is from Maddie, and her question and resonates with me because I plan living to 100 as well. Have you got any advice for someone who's likely to live through this for another 60-ish years?
Matt, that's a very serious question, that is, because that's the sort of thing I often think about when I look at my grandchildren. How are they going to cope, and what decisions will they face over the next 60 years when we've all gone? It's a very serious question. What would you, I suppose you could reframe that question in terms of saying, what would you be telling your grandchildren? So if they're old enough to listen to you and pay attention to what you say, what advice would you give them? That's a tricky question. It's easy to give advice to everyone nowadays, all you guys and all my colleagues, etc. We all are familiar with it, and we can all do something. But for the next 60 years, I would welcome hearing what other people might have to say on that matter. It's a serious question, but it's a difficult one. I'm not sure what I'd say to a 12-year-old or a teenager nowadays in terms of climate change. I haven't thought about it, but maybe we should. Yeah.
I'll challenge you and say not maybe we should. I think it's it's imperative that we do. And I think, Maddie, that is Ian's got a response. Maddie, that was a legendary question. Ian?
The other issue there is, again, it's a personal opinion here, is that I worry about the lifestyles that our children and grandchildren will enjoy in the future. It's not guaranteed they'll enjoy things as much as we've had the benefit of. And the issue becomes one, do you really want to overburden them with some more negative news or negative talking about negative things, given that they'll have enough on their plate as it is? You can educate them, but you don't want to again overburden them with too many negatives when they're looking forward. You'd hope that you don't want to dampen their optimism about the future, is I suppose what was the thing I'd be careful of doing. Yeah, so that's my personal view, but it's a really serious question. Thanks for it.
Maddie, you wanted to quick response?
Yeah, it was just mostly like, I don't know, I have a lot of climate anxiety, so rock bottom anyway, can't be any worse. So that's my personal opinion.
I think thanks very much for that, Maddie. And I can't recall the exact quote. I'll have to find it. But I think that the more information you know, that there's this great, and I can't recall the effect. The more information you know, you realize the least you know. But I think also what that does, it arms you to be able to have conversations with people and make change and advocate for change. And again, kind of reinforcing or putting a plug in for a NECA session, we will be talking about that. Don't let the climate anxiety beat us down between now and Anika. But yeah, and for those that did actually get a copy of Anika's book, you may have already kind of thought through some of this stuff. So Maddie, thank you very much for that question to end this evening's webinar on. Ian, I would like to kind of echo a couple of comments that I've already said, but I'll echo them again that have come up in the chat box, in that everyone's really appreciated your candor and your honesty. And whilst the truth has been a bit of pill to swallow, I think it's a pill that it's a bit like Maddie's question. It's a reality that we need to face. Otherwise, we're going to keep on that. I can't recall which was the colour of the trajectory, the least desirable trajectory. I've probably read. We actually need to start talking about this like it matters, because it does. So thank you very much, Ian. I think that's all. I'll just check my little run sheet. Thank you. I won't recap. I'll just say looking forward to seeing everyone online from just before we'll kick off at 9 o'clock next Tuesday. And any other updates will come via my Mighty Networks. And yeah, have a wonderful long weekend for those of us online that are in WA. Thanks very much, Ian.
Thanks, everyone.